Ah, for the good old days. Wasn't that a beautiful Model T? And then again, wasn't that a beautiful BMW? It all depends on your point of view. One thing is for certain, the old cars were easy to repair. Well, things have changed. Added conveniences and government regulations, anti-skid and airbags, four-wheel drive and four-wheel steering, even environmental temperature control. The method? Electronics, computers, the little black box.
The Corporate Training Department of Standard Motor Products presents this video training program as part of our continuing effort to keep you up to date on how to repair today's cars and remain profitable. This standard electronic engine controls training module covers the Toyota electronic engine control system. In order to confidently and profitably repair these systems, the mechanic must have certain hand tools and test equipment. Also, he should have a working knowledge of the basics of electronic engine controls and have an understanding of engine computer control systems. He should also be familiar with the concepts of open loop and closed loop. And most important, he should be familiar with electrical and electronic diagnostic procedures.
By now you're probably wondering, where is this program going? What will I learn? I don't work on import cars. Well, you're not alone. Many mechanics might say they don't work on import cars, but what is a Ford Probe? Who makes the Chevy Nova? It's probably safe to say that aside from factory dealers or import specialists, the average mechanic does not feel comfortable with what he knows about import cars. So as you follow along with this video program, we will provide all the necessary information to profitably repair the Toyota electronic engine control system. Ready?
The Toyota system you will see can be as easy to repair as the average Ford or Chevrolet. Late model Toyotas are equipped with an onboard diagnostic system to assist you in troubleshooting. Before we actually begin diagnostics and repair of the Toyota engine control system, what is the system trying to accomplish? What does each of the components do? How do they interact with each other to affect the operation of the vehicle? Well, the main objective of this system is to allow the vehicle to give good fuel mileage and clean emission, but not at the sacrifice of good acceleration and smooth operation. Toyota Computer Control System, TCCS, has been used extensively throughout the Toyota model lineup since 1984. As a note, the information and procedures outlined in this program are directly usable on the Chevrolet Nova with the Toyota dual overhead cam 1.6-liter MR2 engine. We will begin by reviewing the operation and function of the engine control system. Then, we will look at the system's components and how they relate to each other and the engine control computer. The central control system is the ECU, or electronic control unit. The ECU takes sensor readings that monitor various engine functions and responds with signal outputs to various control devices. The ECU controls three primary areas. 1. The ignition system. 2. The fuel control system. And 3. The emission control system. The ECU also monitors itself, and if a computer malfunction happens, it switches to failsafe. This operation mode will allow the engine to run, but with very poor drivability. The ECU can be found in various locations depending on the year, make, and model. The diagnostics display is the check engine light located on the dashboard. The light is also designed to alert the driver of a component malfunction. It is also utilized in conjunction with the onboard diagnostic system to display trouble codes. Let's take a closer look. The ECU receives sensor input readings from an airflow meter, an inlet air temperature sensor, a throttle position sensor, a water temperature sensor, a distributor signal for engine RPM, except in the 7M GTE Supra engine where a cam position sensor is used, an exhaust gas oxygen sensor, and a series of miscellaneous switches, air conditioning, automatic transmission, etc. The ECU responds with signal outputs to the electronic fuel injection, EFI, the idle speed control system, ISC, an electronic control transmission, ECT, electronic spark advance, ESA, exhaust gas recirculation, EGR, and the check engine light for self-diagnostics. A quick look at Toyota's electronic fuel injection system shows that it is made up of an air filter and ducts, a vane airflow meter, a throttle position switch, a throttle body, and an air plenum. The system has a fuel pump mounted inside the fuel tank in a very fine micron filter. Fuel then flows through the fuel rail into each of the individual injectors. Excess fuel not used by the injectors then flows through the pressure regulator and back to the tank. Also, the system contains a cold start injector and thermo time switch. The computer's sensor inputs control the fuel injection system in two modes of operation. One, open loop mode, where the fuel injection pulse width is controlled by the computer without an input from the engine's oxygen sensor. The second control mode of the fuel injection system is in a closed loop configuration. Basic input signals from the engine's distributor or camshaft position sensor supply an RPM signal. The airflow meter and inlet air temperature sensor supplying a signal on the mass of the incoming air, a throttle position sensor, and the exhaust gas oxygen sensor. These inputs, operating in a feedback loop with the ECU, determine injector pulse width to minimize emission and increase drivability. The emission control system contains no surprises. A very conventional evaporative emission system is utilized to trap fuel fumes in a charcoal canister. The EGR system is also fairly conventional in its layout. It contains the EGR valve, an EGR vacuum modulator, and a temperature-controlled ported vacuum switch. The ECU, utilizing a temperature control signal, an RPM signal, and throttle position signal, sends a controlling pulse to the EGR control solenoid. The other components of the emission system include a PCV valve, a dash pot, tri-catalyst, and an air injection system. The third system controlled by the ECU is the ignition system. The timing functions can be either by centrifugal, vacuum, or electronic. The electronic spark advance, or ESA, is controlled from basic sensor inputs to the ECU. Input is supplied from the distributor or cam position sensor, engine RPM, the airflow meter, a water temperature, throttle position switch, and the vehicle speed sensor. These signals are compared to the computer's program. A signal output is used to optimize ignition timing by controlling the igniter assembly and therefore the coil's primary feed. Now, to briefly review some of the components in these subsystems. We can see that the airflow meter is the basic Bosch-style vane airflow meter. It uses a thermistor for an inlet air temperature signal and a door which moves in response to the flow of the incoming air. As the door moves, it moves the potentiometer. A voltage signal from the position of the door supplies the engine computer with the information about the amount of the incoming air. Toyota utilizes two throttle position sensors, one on vehicles without electronic controlled transmission, ECT. This throttle position sensor is a simple switch with two sets of contacts. One set supplies the voltage to the computer signaling idle position, and the other supplies the signal when the throttle is fully opened. Obviously, in this type switch, we have only three possibilities: idle, run, and full throttle. The second style of throttle position sensor is used with those vehicles with electronic controlled transmissions. This style switch should be familiar to most mechanics, as it is similar to that used by Ford and General Motors. The switch is a variable resistor or potentiometer. In addition, it has a switch to signal idle position. There are four different distributor or ignition styles. One is conventional style, that is, no high output spark or HEI. It consists of a conventional ignition coil, an igniter or microprocessor which controls the coil's primary current flow, triggered by an ECU signal. Inside the distributor, both centrifugal as well as vacuum advances are utilized, along with single or multiple magnetic pickups. A second style system is used on lean burn engines. This style places the ignition coil and igniter inside the distributor, not unlike a General Motors HEI system. Additional control of the ignition timing is supplied by the computer. The additional timing control takes place in conjunction with the fuel injection system. When the extremely lean fuel mixture of lean burn is called for by the computer, leaner than 14.7 parts of air to 1 part of fuel, additional spark advance is also applied. This timing override takes place when the ECU signals the igniter to advance the timing. The system will increase fuel economy and drivability under extremely lean conditions. A third style ignition system allows the TCCS computer to take control of the ignition timing, no vacuum or mechanical advance. It utilizes an HEI style ignition coil mounted in the distributor cap. A special distributor cap, rotor, and wires are used to insulate the system, as a very high secondary voltage is used. The fourth style system is utilized by the Supra with the 7M GTE engine. This system is a direct ignition style. 3 separate ignition coils, no distributor, and no spark plug wires. The TCCS computer controls all ignition timing functions. The timing signal is generated by a camshaft position sensor signal directly to the TCCS computer.
That's it. We have covered the basic components and functions of the Toyota TCCS system. Now, to repair some common problems. Hands-on experience may be the best teacher, but through the use of video, we can simulate everything except your hands actually touching the components. Ready to begin?
This Toyota is similar to all 4-cylinder Toyotas utilizing the TCCS system since 1984. The owner of this Corolla has been complaining of occasional difficulty in starting. The problem seems to be intermittent. Recently, the vehicle has exhibited a tendency to stumble or hesitate off idle. That is, when he takes off from a light and applies the throttle, the engine seems to sag and then accelerate. He states this is similar to a problem he used to have, and they always change the accelerator pump in the carburetor. What is the first step? What do we look for? Even though you don't work on Toyotas very often, and in fact you prefer to work on Chevrolets, don't turn the car away. As you follow along with this program, you will see that it is not any harder to repair this Toyota than any domestic car. The first thing we need to do is follow a logical approach to troubleshooting. Ask the customer some general information, especially the exact year, make, and model. The engine style is very important. Ask the customer the questions necessary to determine exactly what the complaints are. Remember, you cannot diagnose a problem that does not exist. Keep in mind that the self-diagnostic system in this vehicle cannot troubleshoot everything. There are certain things that should be checked visually or with some simple test equipment, like a volt-ohm meter, before beginning to work on the computer system itself. Considering a no-start situation, or at least an intermittent one, we should first check the ability of the starting system to turn the engine over. Check the battery leads, and cranking system. Remember to always check the obvious. Always check the air filter, coil lead, spark plug wires, and the engine's cooling system. Don't forget, many of the sensors and vacuum control switches that feed the system are dependent upon accurate temperature signals. If the coolant level is low or the antifreeze ratio is off, false information can be supplied to the ECU. A no-start situation and a hesitation. Could it be ignition? Could it be fuel? Well, obviously, since there is no carburetor to look down, it isn't easy to determine if the vehicle is getting fuel. The easiest method to troubleshoot this vehicle is to utilize the onboard diagnostic system first and eliminate those problems with trouble code readouts. Even though Toyota says that the system will display a check engine light when a hard code has been set, be aware of the fact that the check engine light does not always remain on. Do not rely on it. Check the system for codes anyway. Locate the diagnostic connector. Position may vary by year and model. In many models, it is a yellow plastic open-ended female plug, occasionally having a rubber cap over it. In other models, it is a black plastic female plug with a hinged cover. One of the most difficult portions of diagnosing a Toyota is locating the exact position of the check engine connector. As a suggestion, consult the owner's manual. Toyota is very conscious of voltage spikes or feedback loops in their electronic control system. Before working on the TCCS system, always make sure that the ignition switch is off prior to disconnecting any of the electrical components. Never short or ground out connectors unless specifically told to do so in diagnostic procedures of service literature. Now, to access trouble codes. First, turn the ignition switch to the on position and observe the check engine lamp. Then start the engine. Make sure that the check engine lamp lights with the key on and goes out shortly after the engine is started. If it does not, do a quick check of the diagnostic circuit itself, following service literature recommendations for the particular model. Though it is rare, on occasion, a malfunction in the diagnostic portion of the computer can occur. Once the engine has reached operating temperature and has gone into closed loop, turn off the engine. Then turn the key on and connect a service wire, a simple jumper wire, across the specified pins on the check engine connector. On those vehicles with the multi-pin check engine connector, you normally jump connectors T to E1. Pin data is supplied on the inside of the protective cover or in the owner's manual. You should note that certain early model vehicles require the use of a high impedance analog voltmeter to access trouble codes. They do not utilize the check engine light. Depending on the year, make, and model, the number of trouble codes varies, as well as the relationship of the trouble code number and the problem. Always consult service literature for the appropriate trouble codes, diagnostic connection, and system schematic. With the jumper wire installed, let's monitor the check engine light. A 6 and a 10. The 6 indicates that no NE or G RPM signal is being received by the ECU within seconds of the engine starting, or no signal when the engine speed is over 1500 RPM. This code is triggered by a problem in the distributor circuit or magnetic pickup. Also, the igniter or the power feed from the main or EFI relay to the igniter. The 10 trouble code indicates no start or STA starter signal has been received by the ECU when the engine is running over 800 RPM. This code can be set by a problem in the starter circuit, main engine relay, or the ECU itself. Let's continue our logical approach to troubleshooting and pinpoint the exact location of the problem. It is important to consider the fact that the no-start situation is intermittent, but that the hesitation or stumble or tip-in problem shows up consistently. Since this vehicle has electronic spark advance, it has 2 magnetic pickups in the distributor, an NE pickup, RPM. This reluctor has 4 teeth, and a G pickup, crank position. This reluctor has 1 tooth. Using a non-magnetic feeler gauge, measure the air gap between the signal rotor and the pickup coil projection. The air gap should be 0.2 to 0.4 of a millimeter, or 0.8 to 16 thousandths of an inch. Next, utilizing a high-impedance digital volt-ohm meter, measure the resistance of the pickup coils. Disconnect the 2 harness connectors at the distributor, one to the signal generator. Measure from G to G-. We are looking for 140 to 180 ohms maximum. On the second connector, the NE signal generator resistance between NE plus and NE minus should be between 140 and 180 ohms. The pickups check out good. It is suggested that you wiggle the harness to assure that there are no loose connections or broken wires inside of the insulation. As you can see from the schematic, both pickup coils feed a signal to the ECU. The G pickup coil is wired directly. The NE pickup coil feeds the igniter and then the ECU circuit. What other components are involved in both starting the engine and could influence a hesitation? With the cap reinstalled, check the ignition timing function to verify that the ESA works. The electronic spark advance system should vary the ignition timing as a function of RPM. To check the timing, use a service wire and jump terminals T to E1 on the check engine connector. The engine RPM should be approximately 800 RPM with the jumper wire in place. Since it is a little high, it should be readjusted. Timing should be at 10 degrees before top dead center at 800 RPM, transmission in neutral. If the timing needs to be adjusted, loosen the two bolts on the base of the distributor. Rotate the distributor. Retorque the bolts. Remove the jumper wire while monitoring the ignition timing. It should advance to 16 degrees before top dead center. If it does not, it means the electronic spark advance is not working. What would cause no increase in timing? Either the igniter or the ECU assembly itself. Let's check the igniter. For the electronic spark advance to function properly, there should be a signal from the ECU to the igniter to control the primary field of the ignition coil. That signal is located on terminal IGT in the ECU unit. With the engine idling, check the voltage between IGT and E1. It should vary between 0.7 and 1 volt. Since we have 0 volts available, check the ECU terminal, IGT, and the ground. Again, we have no voltage. Since we have already verified that the distributor is good, the problem is either a bad connection in the wiring between the distributor, igniter, and the computer, or a bad igniter. Replacement of the igniter is an easy task. Always turn off the key before disconnecting the igniter wiring. With the igniter replaced, we seem to have found a cure for the hesitation. That is the lack of timing advance. But have we cured the intermittent starting problem connected with code 10? Remember, the 10 indicated a no STA starter signal received by the ECU once the engine has been running at over 800 RPM. Could anything have influenced the failure of the igniter? Before proceeding with road testing the vehicle, we should continue troubleshooting to find what influenced the igniter malfunction. Let's consult the schematic again and see what feeds power to the igniter. As you can see, the power feed for the igniter and coil assembly comes through the engine main relay. Power is fed to the relay field coil by the ignition switch through the computer's 7.5 amp fuse. Would a bad contact or a high resistance contact in the engine main relay affect the engine operation or starting of the vehicle? Yes. It is in the igniter's power path and the ignition coil's primary power path for starting. Also, intermittent contact may create voltage spikes that would affect the igniter. Toyota publishes field winding resistance specifications for the relay. Generally, the field resistance should not exceed 60 ohms, but our problem probably is a bad relay contact. The lowest possible resistance is what we are looking for. Pitted contacts create a voltage drop and increase the current flow through the igniter. The best way to check the resistance would be to energize the relay and measure the resistance from pin 4 to 5. But this may not always be practical. Another way to verify the voltage drop across the relay would be to disconnect the ignition coil and the igniter harness and measure the voltage drop to the ground at that point. You should receive full battery voltage. Using an ohm meter, you could check the resistance across pins 4 and 5, approximately 20 ohms. If we energize the relay contacts by applying 12 volts, you can see that the resistance readings change as we make contact between 50 and 100 ohms. This relay should be replaced. The points are oxidized or burned. We have located the second problem in this ignition system. With the relay replaced, start the engine and allow it to come to operating temperature. Recheck the electronic spark advance. Install the jumper wire across terminals T and E1 at the check engine connector. Idle RPM should be at 800, and our timing should be at 10 degrees before top dead center. Once the engine is stabilized and our timing light is in position, remove the jumper wire. It immediately advances to 16 degrees before top dead center. This indicates that the electronic spark advance is working properly. Turn off the engine and cancel the diagnostic codes. In this vehicle, remove the 7.5 amp AM2 fuse located in relay box number 2. This fuse panel can be found in the engine compartment on the left side of the vehicle. Remove the fuse for approximately 10 seconds. Toyota states the lower the temperature, the longer the fuse must be left out. Remember, this is with the ignition key off. In a Corolla of the same year with the same engine, the procedure calls for removing the 15 amp stop fuse located in the driver's kick panel for more than 10 seconds. Canceling codes in a Camry in the same year requires removing the 15 amp EFI fuse. This fuse is located in the left front corner of the engine compartment, just behind the headlight. As you can see, Toyota is not consistent in the location or the size of the fuse powering the ECU and ignition system. It is strongly suggested that you consult the appropriate service literature or the owner's manual in a particular vehicle for the exact procedure in clearing trouble codes. Cancellation can also be accomplished by removing the negative battery terminal for approximately 15 seconds. But remember, every computerized component in the car will lose memory. That includes the clock, automatic temperature control system, etc. All those accessories will have to be reset. After cancellation of the trouble code has been completed, perform a road test to verify the customer's complaint has been corrected. Also, if the check engine light was remaining on, it should be off at this point. Now that we have successfully completed the repair on a component with a trouble code readout, it should be mentioned that not all components that affect the operation of the vehicle have trouble codes. Also, that trouble codes vary by year, make, and model. Normally, the later the model year, the more trouble codes that are present, and in many cases, California vehicles have additional trouble codes. Probably the most difficult portion of the diagnostics has to do with the vehicle not meeting emission standards, or those problems that are caused by a component that does not have a trouble code. A good illustration of this would be a federalized vehicle with an EGR system malfunction. Early vehicles and non-California vehicles do not contain an EGR system malfunction trouble code. The function of the EGR valve is to reduce NOx emissions. This happens when the exhaust gas recirculation valve is open. It bleeds a portion of the exhaust into the intake manifold to lower the maximum combustion temperature. If the valve malfunctions, it can cause both drivability and emissions problems. If there is no trouble code readout, how do you diagnose the problem? The ECU receives the distributor signal input to control the EGR. Also, a temperature-controlled ported vacuum switch is used. Since this is a back pressure style EGR valve, as long as the exhaust gas velocity is sufficient to build pressure on the bottom side of the EGR diaphragm, the temperature is correct and engine RPM is above specified speed. The exhaust gas recirculation valve should be modulating exhaust gas into the intake manifold. It is quite common for Toyotas to experience plugging of the ported vacuum switches and the throttle body vacuum ports. Each EGR system will vary by year, make, and model. You must consult the appropriate service literature for exact specifications. As a hint to troubleshooting, the onboard diagnostic system can check a lean and rich fuel mixture. It can be utilized to troubleshoot an EGR system, an air pump system, and any other component in the engine besides the fuel system that affects the emission output of the vehicle. The computer is sensitive to CO readings, and the lean and rich trouble codes will trigger when the engine is out of specification. Since this program was designed to deal primarily with the engine control computer as it relates to ignition and emission, those problems associated with the fuel system are discussed and diagnosed in the High-Grade Fuel Control Systems training program on Toyota.
This concludes working on the Toyota computer control system. As you have seen, it is easy to troubleshoot and repair utilizing onboard diagnostics. I would like to take this opportunity on behalf of Standard Motor Products and its training department to thank you for purchasing this training program. And we hope you will consider us for your future replacement parts needs.